we are presented with a DC machine question. I'll read the question for you. A DC shunt motor runs at 1200 rpm on no load, drawing 5 amperes from 220 volt mains. Its armature and field resistances are given. When loaded, the motor draws 62 ampere from the mains. What would be its speed? Assume that armature reaction demagnetizes the field to the extent of 5%. Also, calculate the internal torque developed at no load and on load. What is the motor shaft torque at load? Now this torque drives the mechanical load. So this is the question that we are presented with. Now we'll solve this one. So we'll draw just a rough sketch of how the machine would look like in a load. Okay. So machine at no load. Alright, so the machine at no load they have a DC shunt machine which would, just a rough sketch of the machine, how it would look like. Now it is given that it is driven by 220 volt supply, okay, and this is RF, this is RA, okay. So I'll just write the given quantities, okay. So RF is equal to 110 ohms and RA is equal to 0.25 ohms. Okay, so and it is drawing, it is given IL is given as 5 amperes. So basically this is 5 amperes. Now we can, so the current is moving here. This is the field current and this is the armature current. So if we calculate the field current is nothing but V by RF, which is equal to 220 divided by 110. Okay, so this comes out to be 2 ampere. Okay, so now in this, if this is 2 amperes, so this would mean that armature is drawing 3 amperes, that is nothing but 5 minus 2. Okay, so IA we have now. So now we'll see, it's a simple thing. We'll calculate EA naught, the EMF generated at no load. Let us write it as NI. Okay, so this V, or rather it should be V minus IA RA. So this is 220 minus 3 into 0.25. Okay, so this comes out to be 219.25 volts. Okay, so we have the value of EA and L. Now let us straightforwardly calculate the no load torque. Now we have EA, we know IA, and we have the speed at no load as well. Now speed at no load I have not written here. Speed at no load, let's write it as N naught. It is 1200 rpm. Alright, so we know that now torque at no load is EA NL into IA NL. That's also denoted by NL, okay, divided by omega NL. Okay, so we'll put in the values here simply. So 219.25 into 3 divided by 2 into pi into n. This is 1200 divided by 60. Okay, so the TNL comes out to be 5.23 Newton meters. Okay, this is the value of, so this is the value of TNL and this is the value of EANL. Okay, so now here simultaneously here we will now assume the machine, no, not assume, the condition that the machine at here we should write full load. Okay, the machine is now running at full load or its rated capacity. So similarly we'll draw the sketch. Now the field current, it will remain the same. Okay, field current will remain the same. Now it is driven by the same DC voltage supply. Now it is driven by the DC voltage supply. Now the value of RF is same. The IF will remain same as equal to 2 amperes. Now it is given that it is drawing 62 amperes. So IAFL will be equal to 60 amperes. Okay, so similarly here if we calculate EAFL, it would be nothing but 220 minus 60 into 0.25. So quickly it is now coming out to be 205 volts. EAFL, that is what it is. Alright, so now if we want to calculate the torque, now the torque at full load is again EAFL into IAFL divided by omega FL. Now we see from here that we don't know. This value is unknown. We have to find this value. So we'll find this value. We'll use the term. We'll use this expression. EA is proportional to K phi into N, where this is the EMF, this K is the machine constant, phi is the flux per pole, and N is the speed. Okay, in RPM definitely. Okay, so we don't have to bother about the machine constant will remain definitely constant, flux is constant with load because the machine is shunt type, so the flux per pole, the field will remain the same. So now we have two equations, so we'll calculate it. So similarly we can write EAFL upon EANL, okay, which is K phi. Now K phi into N. What was the N? We have to find out, right? Though we have to take one more thing into consideration, that here in the question it was given that the armature reaction demagnetizes the field by 5%. So I just told you that the field would remain constant if the magnetization, if we do not consider armature reaction. Now the question asks us to consider armature reaction, so it will demagnetize the field by 5%, though the flux per pole will reduce by 5%. So we'll now be remained with 0.95 of phi, and we have to find the value of N at FL. So this machine constant will be the same, in case of no load, and we have been given the value of N. So we'll cancel it out. So from this, N FL, it would come out to be 1181 RPM. Now this is known, so we can definitely calculate, right? Here we have found out this one. EA FL is this value. Okay, so we have this value also now. So now we can find out the torque. Now we can find out this value. So the torque at full load is equal to EA FL IA FL by omega FL. So the TFL is equal to 205 into 60 upon 2 pi into 1181. So the TFL comes out to be 99.45 Newton meters. Now, are we done with the question? Not yet. Why? Because we need to find, now we have this value and we have already calculated the value of T0, or we had called it TNL, which was nothing but 5.23 Newton meters. Alright. So what would be the shaft torque? Shaft torque is nothing but TFL minus TNL. Okay, this is the torque which will drive the load. So the T shaft is equal to 99.45 minus 5.23, which is 94.22 Newton meters. Okay, so we had found, so this we had to found, and we had to find NFL, which we had found. We had to find torque generated at no load. Okay, so we had found all the quantities, and this is how the question looks. I will include the solution of this question in the description box. Thank you for watching. We will meet in the next one.
Hello everybody, welcome to Express Electrical. I hope that you liked the video. Yes, I admit the problem was very simple, but you know what, we're just getting warmed up here. And every problem is a problem until we solve it. So that's the idea. So the idea here is to encourage you to learn basic concepts through problem solving. And I think that we tend to devote less time in solving numericals. So idea is to encourage you to solve more problems, solve more numerical problems, and just see how we approach a problem and how we solve it. As we know that engineering is an applied field, and problem solving becomes naturally important and most useful to us as engineers, because it would help us to approach the real world engineering problems when we face them in our real lives. And it's my personal experience that, and I think you'll agree, that more clarity on a given concept is achieved when we solve numericals related to them. When we understand a particular thing, we need to apply it somewhere to understand it. So just solving a problem is just like application of that concept into a certain thing, So we'll keep throwing at you some good quality problems from electrical engineering, from all the subjects, from all the basic subjects, and to be it machines, power electronics, power systems, basic circuits, and electromagnetics, and we'll just keep throwing you with some good quality problems and with simplified authentic solutions at regular intervals, hoping that this will help you in whatever minuscule way possible in your respective learning process. We must feel proud that being electrical engineers, we witness how a given subject has evolved itself, be it electrical machines, be it transformers, be it power electronics, and the whole idea of having the very fast converters and inverters, the control systems. And we should appreciate the giganticity and the beauty of the scientific breakthroughs of Mr. Faraday or Mr. Tesla or Mr. Maxwell. I mean, it's totally mind-blowing and very beautiful indeed. And I would also confess that I do not claim to be any expert in the field. I mean, nor you have to be any expert to solve, I think, any normal undergraduate level problem. And I'm not decorated with very beautiful credentials, so you can consider me your fellow learner, a partner in your journey. And I'm gratified that you invested your valuable time being part of this learning process with me, and I hope that you keep working hard towards your goal and do not stop until you achieve them. If you feel that this video has helped you add certain value to your knowledge in any way possible, then you might consider liking and subscribing to the channel. And if you wish that something is incorrect and something needs improvement, you may kindly indicate the same, and it would most certainly be appreciated. Thanks for watching, and see you with another problem in the next.